Welcome back to Very Ordinary Differential Equations. In this lecture, we learn how to take the Laplace transform of a step function. Now, the Heaviside function, h of x or u of x for unit step function, is a piecewise constant function which is used to represent a sudden change in value. Specifically, when x is negative, u of x is 0, but suddenly, when x is bigger than or equal to 0, u of x changes to a value of 1. So if these are our coordinate axes, here we see in blue that for x being negative, the value of the function is 0. But when x is bigger than or equal to 0, the value of the function is 1. So there is this sudden jump or step at the value x equals 0. Now we can perform a horizontal shift of this function to change when this jump occurs. And this sudden change from 0 to 1 is commonly used to represent something changing from off to on or suddenly appearing at a certain time. So if we simply perform this change, u of t minus tau, we horizontally shift our unit step function by tau, meaning for t less than tau it is 0, but suddenly at the value tau it changes to 1. And again, here are our coordinate axes with this shifted step function. For a positive value of tau, we have shifted to the right by that amount, and now we just have this unit step occurring at an arbitrary time. Now we can take a product of a step function with a continuous function f to represent something which is piecewise continuous. So u of t minus tau times f will represent a function which suddenly appears at this time. Because when t is less than tau, the step function is 0, so regardless of the value of f, 0 times that will be 0. But when t is tau or larger, u of t minus tau is 1, and we simply get the function f of t. So here is an example of that. Okay, so again, we have our coordinate axes, and then the step function has been shifted to the right by tau. To the left of tau, the step function is 0, so the product is 0 anyway. To the right of tau, the step function is 1, so the product simply spits out the value f of t, which is whatever continuous function we had. And in fact, we can use this approach to generate something which is a piecewise continuous function with many pieces. So here's our set of coordinate axes. Now here is a piece of a continuous function starting at 0 and ending at tau 1. And then maybe there's another continuous function in between tau 1 and tau 2, and another continuous function from tau 2 to tau 3, and so forth. But how are we going to represent a crazy mess like this as an approachable sum of various products? So here's an example of the type of function we want to be able to represent. Now we can write this in a piecewise manner. So f of t in between 0 and tau 1 is given by f naught. In between tau 1 and tau 2, it's given by f1. In between tau 2 and tau 3, it's given by f2. And in this picture, for all t larger than or equal to tau 3, it's given by f3. So this is a standard way to write a piecewise function, but we want to be able to write it in terms of these step functions. Okay, so we can write it as f naught of t. Now that covers everything from 0 to tau 1 perfectly accurately, but after tau 1, it's no longer accurate. So we can add in something like this. Now this second term, to the left of tau 1 is 0 anyway, because this step function is 0 to the left of tau 1. To the right of tau 1, I now get f1 minus f naught. These cancel and we get f1. So between these two terms right here, from 0 to tau 1, we will get f naught, and then suddenly, past tau 1, we will get f1. But now we need to account for what happens from then on. So we could do this. Okay, so to the left of tau 2, this term is doing nothing anyway. To the right of tau 2, it simply cancels the f1 that we had and introduces f2. And then to the right of tau 3, we can cancel the f2 and introduce f3. This is our general framework for representing a piecewise continuous function in terms of step functions. Now, if we can compute the Laplace transform of something of the form a step function times something else, then we can apply that result to taking a Laplace transform of something of this form, because it's a sum and Laplace transforms are linear. Over here, it's really not clear how to take the Laplace transform. Over here, linearity comes in handy. So let's get to work computing the Laplace transform of the product of a step function with another function. We're specifically going to assume that tau is positive and that f is a function that has a Laplace transform. Then we're going to go ahead and set up the integral for the Laplace transform. We integrate from 0 to infinity e to the minus st and then the function that we're taking the Laplace transform of, the step function times f. Now how does that step function behave? When t is less than tau, it's 0. When t is bigger than tau, it's 1. So we split our integral into two pieces accordingly. When t goes from 0 to tau, the step function is 0. But when t goes from tau onward, the step function is 1. Now that left integral is just 0, because we are integrating 0 on a nice finite interval. And on the right, we just have e to the minus st f of t. This is very close to being the Laplace transform of f, but the bounds of integration are wrong. The integral starts at tau rather than at 0, so we're going to do a change of variables. If we replace t with t plus tau, we just have to ask how that affects the bounds of integration. In this integral, when the variable is tau, that corresponds in this integral to the variable being 0, and then it increases from there. So once we factor out e to the minus s tau from this integral, the variable of integration is t, so e to the minus s tau is effectively a constant and can be factored out. Now what do we have? The integral from 0 to infinity, e to the minus st f of t plus tau, which is exactly the Laplace transform of a shifted version of f. It's the Laplace transform of f of t plus tau. And this gives rise to something that we call the second shifting theorem for Laplace transforms. So here's the result we just proved. The Laplace transform of a step function at tau times f of t is just an exponential e to the minus s tau times the Laplace transform of a shifted version of f. We rephrase this as the following theorem. The proof is very quick. We're just going to define g of t minus tau to be f of t. Equivalently, f of t plus tau is g of t, and make some relevant substitutions. Here, instead of f of t, we call it g of t minus tau. Here, instead of f of t plus tau, we call it g of t, and the theorem is proved. That's it. Now, the utility of this second shifting theorem comes to inverse Laplace transforms. If capital G of s is this Laplace transform, L of g of t, then here we have e to the minus s tau, capital G of s, which is the Laplace transform of a shift function times g of t minus tau. In other words, if we know an inverse Laplace transform to something capital G of s, then if I multiply capital G of s by an exponential of the form e to the minus s times a constant tau, so this is something whose inverse Laplace transform I know, and it's being multiplied by e to the minus s constant. The inverse Laplace transform of all of this would simply be a step function times g of t minus tau. Let's take a look at an example. Let's compute the Laplace transform of this piecewise continuous function. From 0 to 4, the function is 1. From 4 to 7, it is 5t, and beyond 7, it is 3t squared. So we're going to write f in terms of unit step functions. So here we have it. It begins with a value of 1. At 4, we cancel out the 1 and introduce 5t. And then at 7, we cancel out the 5t and introduce 3t squared. So if I take a Laplace transform, first we simply apply linearity by distributing the Laplace transform across this sum of three different terms. Now each of those two terms to the right, we're going to use this formula right here. The Laplace transform of a step times a function is e to the minus s tau times the Laplace transform of a shifted version of that function. So first, the Laplace transform of 1 is 1 over s. That's straightforward. Here we have u of t minus 4 times 5t minus 1. So we extract an e to the minus 4s, and now instead of taking the Laplace transform of 5t minus 1, we would have the Laplace transform of 5t plus 4 minus 1. Similarly here, we extract an e to the minus 7s, and instead of having the Laplace transform of 3t squared minus 5t, it would be 3t plus 7 squared, 5t plus 7. So we distribute out those things in parentheses. So now we have 1 over s plus an exponential times one Laplace transform and another exponential times another Laplace transform. So here's where we are. The Laplace transform of this piecewise continuous function is 1 over s plus two terms that are products of exponentials with Laplace transforms of polynomials. Those are straightforward enough. The Laplace transform of 5t plus 19 is 5 over s squared plus 19 over s, and the Laplace transform of 3t squared plus 37t plus 112 is 6 over s cubed plus 37 over s squared plus 112 over s. As a second example, let's find an inverse Laplace transform of e to the minus 2s over s cubed plus e to the minus s over s squared plus 1. Now each of these terms looks like an exponential function multiplied by something a little more familiar. Specifically, the first term, 2 over s cubed, very closely matches a formula in any table of Laplace transforms, so factor out a 1/2 to introduce that 2. And 1 over s squared plus 1 by itself will appear in any table of Laplace transforms. So if I hit both sides with an inverse Laplace transform here, we factor that 1/2 out of the first term and otherwise rely on linearity. And now here we have e to the minus 2s, and this we recognize as the Laplace transform of t squared. However, since it's being multiplied by this exponential, we get a step function u of t minus 2, and instead of t squared, it's t minus 2 squared. Similarly, over here, we recognize this as the Laplace transform of sine t, but because it's being multiplied by e to the minus s, we get this step function u of t minus 1, and instead of sine t, it's the sine of t minus 1. There's the second shift theorem in action. As a third example, let's find the Laplace transform of the triangle wave function graphed here. So this graph is composed of various line segments of slope 1. Okay, it goes up with a slope of 1, then down with a slope of 1, up, down, etc. Since it's going from a height of -1 to 1, each time it goes up or down, it takes 2 units of time to do so. So from t equals 0 to 2, it goes up, then from 2 to 4, it goes down, and so forth. We can write this in a piecewise manner, like this. We would just have to find the equations of all of these different lines. Now from 0 to 2, we have the line t minus 1. From 2 to 4, we have 3 minus t. The slope is now -1. Then from 4 to 6, we have t minus 5, and we can keep going in this manner. So here was the graph of our function. Now what we could do is represent the function as an infinite series of various step functions times the next line segment minus the previous one. But that would be a whole lot of work. It's a viable approach, but it gets rather complicated. The function, however, is seen to be periodic with period 4. This function repeats itself after 4 units of time. Specifically, f of t plus 4 will always be equal to f of t. Most tables of Laplace transforms will have an entry that discusses periodic functions. So in most tables of Laplace transforms, for periodic functions, you'll find an entry that looks something like this. When f of t plus capital T equals f of t, then the Laplace transform is given by this definite integral, 0 to t, of e to the minus st f of t dt, divided by 1 minus e to the minus s capital T. It's not actually a terribly difficult result to prove. It's a little bit beyond what we're going to do in detail. If you're very interested in finding why this is true, set up the integral for the Laplace transform of f, and then simply break it up into pieces from 0 to t, from t to 2t, 2t to 3t, and so forth. Perform a change of variables on each one of those to make them all be over the interval from 0 to t, and a geometric series will actually show up. So you'll get a whole bunch of definite integrals from 0 to t, and then a geometric series, and this result pops out of that. But in our problem, we had f of t plus 4 is f of t. So that formula for capital T equals 4 corresponds to this. The Laplace transform is given by the integral from 0 to 4 of e to the minus st f of t dt over 1 minus e to the negative 4s. The numerator just needs to be computed. That denominator is what it is. Now, our function on the interval from 0 to 2, we had f of t is t minus 1. But on the interval from 2 to 4, f of t was 3 minus t. So we're just going to go ahead and compute that integral. So the integral from 0 to 4 of e to the minus st f of t, we split it up from 0 to 2 and 2 to 4 because on those two intervals, the function had two different definitions. We just go ahead and anti-differentiate this. You can already tell you've got t's times exponentials, so some integration by parts is going to be necessary, but here it is. And if you go ahead and plug in the various bounds of 2 and 0 or 4 and 2 and simplify everything you can, you'll end up with this right here. So the integral from 0 to 4 of e to the minus st f of t dt is 1 over s squared times this quantity, 1 minus s minus 2e to the minus 2s plus s plus 1 times e to the minus 4s. Altogether then, the Laplace transform is given by this definite integral over 1 minus e to the minus 4s, and we've computed the value of that integral. It might be possible to simplify this down somehow, but I'm not terribly interested in doing so. Here we have the Laplace transform of our triangle wave function. So altogether, what did we discuss? The unit step function, u of t, which transitions from 0 to 1 at the origin, provides a convenient way to define piecewise continuous functions as sums of various terms involving these shifted step functions. If we can then reinterpret the function f of t as being translated by the same amount, in other words, call it u of t minus tau times g of t minus tau, then we can take the Laplace transform using the second shift theorem. Combined with earlier techniques we've already discussed, this will in fact allow us to solve differential equations using Laplace transforms with piecewise continuous forcing functions, which would otherwise be rather difficult to do without using Laplace transforms.